One thing we haven't really discussed yet is this mysterious lambda value that we can get out of the Lagrange multiplier equations. The lambda is actually called the Lagrange multiplier, and it's the Greek letter lambda, for which is analogous to an L in our regular alphabet. We haven't really looked at it, but it does have a significance. You might wonder, why would we have this value? What would it mean if we did have it? What we can do is dissect it a bit, going back to properties of the gradient. So remember, these double bars mean magnitude. So magnitude of the gradient of f represents the rate of increase, so the slope in the direction of the gradient, or the rate of increase we can find if we move away from a point in the direction of the gradient. And by an exact analogy, the magnitude of the gradient of g would be the same thing, only how does g change? What we set equal here, this was our equation for optimality, which is the Lagrange, the start of our Lagrange equations. We said that the gradient of each of them have to be parallel, or that the gradient is a multiple of the other gradient. Well, we can solve for lambda here and just divide. We can say, let's divide through, well, let's talk about lengths first, because that makes it magnitudes and not vectors. And we can divide magnitudes. So we just put some bars on here, some bars on here, and if everything's positive, then we can divide through by the gradient length of g, length of gradient g, and we get this ratio here. So the scale of lambda is going to be the scale of these two lengths divided by one another. Okay, so what? Well, let's translate this one step further. Lambda gives the rate of increase of f divided by the rate of increase of g. Okay, that's what those two magnitudes meant. Here's the real interpretation. Lambda gives the approximate increase in the optimum value of f when the value of the constraint g is increased by, and we just put this standard step size of 1 here. So if we increase g by 1, we can think of this as a delta f over a delta g. That's probably the easiest way to do it. And the classic example of g here would be a budget constraint. Something like x plus y equals our budget. So we have total budget, we can split it between two sources. Then we can say, oh, well, if I increased my budget by $3 and I have this lambda ratio, I could solve for the change in f when we're done. So how much more would I go up or down if I could change my amount of the constraint? Sometimes it's really important, sometimes it's a little less so, but it's an interesting property to have, and it does give some meaning here to the lambda value. We'll explore this through at least one example.